Hi, welcome to Sunil Maths tutorial, functional analysis class number 53. In this video, we'll learn a definition and followed by a theorem. Let us see the definition. Let capital S be the set of all self-adjoint operators. Capital S be the set of all self-adjoint operators defined on a Hilbert space capital H. Now we define the ordered relation less than or equals to as follows. If a1 comma a2 belongs to capital S and a1 less than or equals to a2 implies as inner product of a1 comma x less than or equals to inner product of a to x comma x. This is true for all x belongs to capital H. This is known as ordered relation defined over the set capital S of all self-adjoint operators. So depends upon this definition, we'll learn a theorem. Let us see the statement. The real Banach space of all self-adjoint operators on capital H is a partially ordered set. Whose linear structure and ordered structure are related by the following two results. If a1 less than or equals to a2, then a1 plus a less than or equals to a2 plus a for every a that belongs to the set capital that belongs to the set of all real self-adjoint operators. And if a1 less than or equals to a2 and alpha is a real number, positive real number, then alpha a1 is less than or equals to alpha a2. Right? We prove this. We start with defining capital S and ordered relation. Let capital S be the set of all self-adjoint operators on a Hilbert space capital H. Capital S is the set of all self-adjoint operators defined over the Hilbert space capital H. Now we define the ordered relation. Less than or equals to on capital S as follows. For a1 comma a2 belongs to capital S, and if a1 less than or equals to a2, which implies as inner product of a1x comma x less than or equals to inner product of a2x comma x for all x belongs to capital H. Now we have to prove that the set capital S with respect to less than or equals to is a partially ordered set. It means the set of all self-adjoint operators is a poset with respect to the ordered relation less than or equals to. So to prove that partially ordered set, we have to show that it is reflexive, antisymmetric and transitivity properties over the set capital S. So first we show that S is reflexive property over capital S. So right, for a1 belongs to capital S, and take an element small x belongs to capital H, we have inner product of a1x comma x is equals to inner product of a1x comma x. This is nothing but inner product of a1x comma x is less than or equals to inner product of a1x comma x, which implies as a1x less than or equals to a1x, which implies as a1 less than or equals to a1 because x not equals to 0. So this condition shows us a1 less than or equals to a1. This condition shows us the set S is reflexive. Therefore, capital S is reflexive with respect to the ordered relation less than or equals to. That's it. Now antisymmetric. The second relation is antisymmetric. Antisymmetric. To prove this antisymmetric, let us take two elements a1 comma a2 belongs to capital S and take small x belongs to capital H. Let us take a1 inner product of a1x comma x less than or equals to inner product of a2x comma x and inner product of a2x comma x less than or equals to inner product of a1x comma x, which implies as this condition implies as inner product of a1x comma x is equals to inner product of a2x comma x, because we learned that x or y, x related to y and y related to x implies as x equal to y. So by applying that condition, inner product of a1x comma x is equals to inner product of a2x comma x, which implies as inner product of a1x comma x minus inner product of a2x comma x is equals to 0, which implies as inner product of a1x minus a2x comma x is equals to 0, which implies as inner product of a1 minus a2 into x comma x is equals to 0, where you observe that x not equals to 0. Whenever this x not equals to 0, obviously a1 minus a2 is equals to 0, which implies a1 is equals to a2. This condition shows us capital S is anti-symmetric. Capital S is anti-symmetric with respect to the relation less than or equals to. So we prove that S is reflexive. We prove that S is antisymmetric. Next you have to show that S is transitive. Transitivity. Third axiom, third property, transitivity. To prove that transitivity, let us take three elements. Let us take a1 comma a2 comma a3, they belongs to S and x belongs to capital H. Let us choose inner product of a1x comma x less than or equals to inner product of a2x comma x and inner product of a2x comma x less than or equals to inner product of a3x comma x. This condition shows us inner product of a1x comma x less than or equals to inner product of a2x comma x less than or equals to inner product of a3x comma x, which implies us inner product of a1x comma x is less than or equals to inner product of a3x comma x, which implies us a1x less than or equals to a3x, which implies as a1 less than or equals to a3. Therefore, we conclude that a1 less than or equals to a2, a2 less than or equals to a3 implies as a1 less than or equals to a3. Therefore, capital S is transitive. Capital S is transitive with respect to ordered relation less than or equals to. Therefore, we conclude that capital S with respect to less than or equals to is a partially ordered set. Is a partially ordered set, which is required one. So the first part is over. A capital S with respect to less than or equals to is a partially ordered set. Next we have to show that the fourth condition, if a1 less than or equals to a2, then obviously a1 plus a less than or equals to a2 plus a for every a. You have to show that if a1 less than or equals to a2, then a1 plus a less than or equals to a2 plus a for every a. So for this, to prove this, let us take two elements a1 comma a2 belongs to S and x belongs to capital H. Let us assume that a1 less than or equals to a2. Let us assume that a1 less than or equals to a2. If a1 less than or equals to a2, then obviously inner product of a1x comma x is less than or equals to inner product of a2x comma x, which implies as inner product of a1x comma x plus inner product of ax comma x is less than or equals to inner product of a2x comma x plus inner product of ax comma x whenever a not equals to 0. Whenever a not equals to 0. So which implies as inner product of a1 plus a x comma x less than or equals to inner product of a2 plus a x comma x. This condition shows as a1 plus a2 into x less than or equals to a2 plus a into x. I'm sorry, here it is a only, okay, a1 plus a. This condition implies as because x not equals to 0, a1 plus a less than or equals to a2 plus a, which is required result. Which is the required result. This is true for all a greater than or equals to 0. A greater than or equals to 0 for all positive operators. For all non-negative operators you can. Next we can show that and the fifth condition, if a1 less than or equals to a2 and alpha greater than or equals to 0, then alpha a1 less than or equals to alpha a2. This is next condition, we have to show that. So right, here also you have to assume the same thing. Let us take a1 less than or equals to a2 and x is a real number, x is an element from Hilbert space and this x not equals to 0. Take a real number alpha which is greater than or equals to 0. Alpha is a real number greater than or equals to 0. Now since a1 less than or equals to a2, so it is obviously which implies as inner product of a1x comma x is less than or equals to inner product of a2x comma x. Now multiply on both the sides with alpha because alpha not equals to 0. Alpha into inner product of a1x comma x is less than or equals to alpha into inner product of a2x comma x, which implies as inner product of alpha a1x comma x less than or equals to inner product of alpha a2x comma x. This condition shows as alpha a1x less than or equals to alpha a2x. Because of x not equals to 0, we conclude that alpha a1 less than or equals to alpha a2. That is the required result wherever alpha greater than or equals to 0. That's it. This completes the proof of our theorem. So remember that the set of all self-adjoint operators defined in a Hilbert space capital H forms a partially ordered set with respect to the relation less than or equals to, and it also satisfies some another two properties, a1 plus a less than or equals to a2 plus a and alpha a1 less than or equals to alpha a2 whenever a1 less than or equals to a2. In the next video, we learn the definition of positive operator and a theorem on positive operator. Keep learning.